Good evening to everyone. Welcome to the third week of the problem solving session for traffic engineering. My name is Sedi Vinayagam. I'm a PhD scholar in the civil engineering department at IIT Madras. Okay, so let's start with an overview of the concepts that we were taught in week number 3 of traffic engineering. Okay, so this week, we were looking at two major, concepts. One was about shock waves, and the other was with respect to queuing analysis, right? So the first three lectures were on shock waves, the last two were on queuing analysis, right? So the first lecture, we had an introduction to shock waves, right? So what are shock waves? So in the previous week, we learned about the traffic stream parameters, right? So we learned about the flow, density, and the stream speed, right? So QKV. So these particular, a combination of these, traffic state variables, traffic stream variables, will define what we call as a traffic state, right? For a given value of density and given value of flow, right? So we have a particular traffic state, right? It's a traffic condition, right? So that we are describing in terms of these traffic variables, right? So that's what we call as a traffic state, right? For example, when we observe jam density, right? So that's one particular traffic state when the flow is zero and speed is zero, and we have the maximum density. So that's one traffic condition that we observe on the road. So that's called the jam density. That is one particular traffic state, right? Similarly, so any combination of these three variables, right? So that will define a particular traffic state, right? So you don't even need three. So any two would suffice. Why? Because these three variables are related by this equation, right? So q is equal to kv, right? So if you tell me the value of q and value of v, so automatically there will be only one value of k that will satisfy this equation, right? So in fact, you only need any two out of these three variables, to uniquely describe a traffic state, right? So that's traffic state. So what are these shock waves? So what these shock waves are basically, so when you have two traffic states that are meeting in the road, so what we so these shock waves will be created. So shock wave is nothing but the boundary that separates two different traffic states in the road. Okay, so shock waves is nothing but a boundary between traffic states. So for a given pair of traffic states, that are meeting, so we will have a boundary that will be separating these two traffic state, and this boundary is what we call as the shock wave. Okay. So next, so in the first lecture, we were looking at how to qualitatively, analyze these shock waves, right? So we have different kinds of shock waves that will be created depending on what are the two traffic states that are, interacting, right? So because when we have a free flow traffic state meeting with a congested traffic state, so we'll have certain kind of shock waves generated and so on. So in total, we have, six types of shock waves, right? So that's what we saw in the qualitative analysis. So these are, frontal, stationary. Then we have forward forming. Then we have forward recovery. Then we have backward forming. We have backward recovery. And then we have rear stationary. Right, so these are the six different types of shock waves, right? And so what determines these six different types is basically, whether these shock wave boundary moves in the direction of the traffic flow or against it, right? So that's what this forward and backward is, right? So if the boundary is moving along in the direction of the traffic state, so you will say that this is a forward moving shock wave. If it is against, it will be a backward moving shock wave. And similarly, the stationary means, the traffic state or the traffic boundary is not moving, it is at a constant position, it's at the same location, then we call it stationary. And forming and recovery is again based on the two traffic states, right? So if a low density traffic state, is in the downstream of the boundary, and high density is on the upstream of the boundary, so we'll call it a forward forming shock wave, right? So for forward forming, so say this is your forward forming shock wave. So to the right, which is to the downstream, you will have a low density, and here you will have a high density. So in that case, you'll have a forward forming shock wave. So under forward, this will be a forward recovery shock wave. So this is not forming, this is forward recovery. For a forward forming, it will be the opposite of this, right? So high density will be on this side, on the downstream upstream side, and low density will be on the upstream side. So backward forming and backward recovery. So backward forming is that shock wave where the Q length grows, right? So and backward recovery is when the Q is the shock wave that will be reducing the Q length. Okay, and rear stationary, forward stationary. So these have zero slope. So they will be at a given location, right? So these are the qualitative way of describing the shock waves. So in the second lecture, we were looking at quantitative analysis, right? So till now we only talked about the direction of movement, or what are the traffic states that are meeting. So we still don't have any numerical way of quantifying these shock waves. So in the second lecture, we were looking at how to numerically quantify it. So for that, we looked at how to determine the speed of shock wave. So what is the speed of shock wave? So as I said, the shock wave is separating two traffic states, right? But this in most cases will not be stationary, and this boundary will move along space and time. So if you take so generally we use the space-time plots. So what is a space-time plot? So you have one axis that describes the location, right? So x, and the other axis that will describe the time, right? So this is our space-time plot. So here, so when two traffic, say we have a forward, forming or recovery shock wave separating two states A and B, right? So what does this mean? So at a particular location, let us say x1, right? And let us say this point is t1. Okay, so for t less than t1, at x is equal to x1, the traffic state is A, right? So at t1 is when there is a change from A to B, right? So this is when the traffic change is happening at location x1, and for t greater than t1, the traffic state at location x1 is B, right? So which means that the traffic state changes at a particular location with respect to time, and also at a given point of time, there is a variation in the traffic state along the along the space, right? So this speed of shock wave is with respect to how these traffic states are propagating, right? So this boundary separating A and B is at location x1 at time t1. At a different time t2, this boundary has moved to some other location x2, right? So at this time t2, so if you look at point x1, immediately upstream and downstream of it, it is only it will be only traffic state in the traffic state will be same, right? So there won't be any difference. Whereas if you look at location x2 at time t2, at this point upstream of it will be traffic state B, and downstream of it will be traffic state A, right? So the boundary has moved to a different location at a different point in time. So this traffic state, this boundary between the traffic state propagates through space and time, right? And how quickly or how, in what direction and how quickly it is moving. So that's what we are trying to quantify in terms of the speed of the shock wave, right? So basically the slope of this boundary, right? So this line which is determining, which is representing the shock wave boundary. So that's what we are calling as the speed of the shock wave, right? So how quickly these traffic states are propagating and in which direction, right? So that's what we call as the speed of the shock wave. So how do we determine this? So if you have the QK fundamental diagram, right? So generally we have a shape like this, right? So when you have two traffic states, so again, as I said, a traffic state is nothing but a unique combination, right? So if I say this particular point A, so it has a particular flow value QA and a particular density value KA, right? So that is one particular traffic state, and let us take another, traffic state B, right? So it has QB and KB, right? So let us take this is the example. So if these two traffic states are meeting, so what is the speed of the shock wave that will be created? So it's basically the slope of the line in the fundamental diagram that connects these two traffic states, right? So if I connect the A and B by a straight line and find out the slope of this, let us say that is the slope is WAB, so then the speed of this shock wave will be WAB, right? So how did we get this? So we looked at it in the lecture. So it's basically coming from the conservation of the flow along this shock wave boundary, right? So the number of vehicles that are moving. So what is happening at the boundary? So as I said, immediately upstream of it there is one traffic state B, and immediately downstream of it there is traffic state A, right? So at the boundary, vehicles are changing from one traffic state to another, right? So the number of vehicles that are leaving from traffic state B should be equal to the number of vehicles that are entering into traffic state A, right? So by using that conservation law, so we found that the slope of this, so WAB will be nothing but QA minus QB by KA minus KB, right? So that is nothing but the slope of this line in the QK fundamental diagram, right? So that's how we derived what the speed of the shock wave is. Okay, so in the third lecture, then we looked at some numerical examples, right? So we did qualitative analysis, then quantitative analysis, then we put those two together, in the form of numerical examples. So where we looked at like different scenarios, right? So when what happens, at a signalized intersection. So what happens generally? So when you have a signalized intersection, so again we have the space-time diagram, right? So X and T. So at a particular location, you have a traffic signal. Okay, so this is your signal location. So what happens in a signalized location? For certain duration, you have green time, so vehicles can pass through, and for certain duration, you will have red time, right, in a cycle. So when vehicles can't pass through, so you are creating different traffic state forcefully, right? So let us assume this particular region is your red duration. Okay, so initially some demand is there, right? So inflow, let us say, into this signalized location is some value A, right? Some traffic state A, right? So vehicles will be passing through without any interruption. So this is having a traffic state of A. But what happens as soon as the signal turns red, right? So vehicles have to stop, right? So they must stop. So therefore, there won't be any flow. So in this particular space time, so during this duration, red duration, the downstream location of the signal will have zero flow, right? So, and what will happen at the upstream location? You will have jam density, right? So because all the vehicles have come to a stop, and you have created a jam density condition, right? So this is, let us say this is state B, right? The jam condition, and this is state C, right? So we have three different traffic states, and there will be traffic, shock waves created when two different traffic state meet, right? So you have traffic state A and traffic state B. So if you look at the fundamental diagram, right? So what is traffic state A? Somewhere here, let us assume it is somewhere in the free flow condition. So B is the jam condition, right? And C is, at the origin, right? Zero flow, zero density. So what is the traffic state between A and B? It is a backward, forming shock wave, right? So that is the, shock wave that will be created between A and B. And what will be created between A and C? So A and C will be at this particular free flow speed, right? So this is at some speed, and then then you have also between B and C. What is the traffic state between B and C? So they are that it will be a horizontal line, right? When you join B and C, so it is a stationary shock wave that will be created. So what happens once the red time finishes? You have again green time starting. So what happens at green time? So you will have flow at capacity or at the saturation flow rate. Why? Because you have enough demand that has accumulated during the red period, and once the green time starts, so all these vehicles will be leaving at capacity condition, right? So that is, let us say that is D, right? So you will have D. So again there will be a boundary that will be found between C and D, right? So that is at somewhere there, and then there will be a boundary between B and D. So that is here. That is again negative, but it is at a smaller slope, or sorry, at a higher slope. So that is your backward recovery shock wave, right? So once when these two shock waves meet, that's where all your Q will be cleared, and whatever comes afterwards can again pass through without any interruption, right? So that's how the shock waves will help us understand the propagation of traffic state. So this is one particular example of a signalized interception, but it can be used to understand any such scenarios where we have this congestion or bottlenecks that are present in the field. Okay, so we looked at that in third lecture. So in the fourth lecture, we went into queuing analysis, right? So here we looked at three different terminology. So that's important to understand and differentiate. So demand, volume, and capacity, right? So what is demand? So we have a facility, road facility, and so demand is basically the number of vehicles that wants to use that facility, right? So that's what we call as demand, right? So what's the demand? It's how many vehicles that wish to cross or use that particular facility. But so what is volume? So volume is what we measure in the field, right? So you go to that facility, you measure how many vehicles are crossing, say in 1 hour, and then so what that measurement will be your volume, right? So that is the observed value, right? So volume is the observed quantity. So is will demand be equal to volume? So number of vehicles that want to use and the number of vehicles that are actually using, right? So D is that are wanting to use, V is that are actually using the facility. So will these two quantity always be the same? So it may or may not be the same, right? So that's where the third term, right, capacity comes into picture. The capacity will determine whether this demand will be equal to the volume or not. So what is capacity? Capacity is the physical limit to what the facility can accommodate, right? So how many vehicles can the facility serve in a particular duration, right? So the number of vehicles that can that can physically travel, so the maximum number of vehicles that can physically cross this particular location, so that's the capacity. So now what is the relation between demand and volume? So demand will be equal to volume if demand is less than or equal to your capacity, right? So if all the people that wants to use the facility can be supported by the facility, then what we will be observing on the field, it will be the same as the demand, right? So the volume will equal to the demand. But if demand is greater than the capacity, then the volume will be lesser than demand. Why? Because say 1,000 people or 1,000 vehicles wants to use a particular road, right? Wants to cross a particular location within 1 hour, but the road can only accommodate 750 people, 750 vehicles, right? So in 1 hour, so what happens? Only 750 vehicles then can cross, right? So that's what we will be observing. If you go to that particular location and count, only 750 vehicles will be crossing. So the rest of the 250, what will happen? So they will be either waiting, so or they can use a different route, or they can cancel the trip. So whatever, it's so we can't say what will happen to those 250, depending depends on the duration of the those particular drivers, right? So what we can surely say is the volume will be lesser because the demand is 1,000, right? So the 1,000 vehicles wants to use, but only 750 can be accommodated, right? So volume will be lesser than the demand. So that much we can say. So that's important to understand what's the difference between demand and volume. So the skew formation happens because of the demand exceeding the capacity, right? So because demand exceeds capacity, all the demand cannot be accommodated. So the excess demand has to wait, right? So if they want to use the same facility, they have to wait, and this waiting will create the queues, right? So the queues will form. So that's what we looked at it. And bottlenecks. So bottlenecks is basically where the locations where the capacity is reduced, right? So either artificially or by the traffic factors, because of that the reduced capacity location. So those are called the bottlenecks. So and finally, in the final lecture, so we looked at two different ways of or two different categories of analyzing the queues. So one is the deterministic way, another the stochastic way. So what is deterministic way? So deterministic, as the word suggests, is so we know all the components that are required for this queuing analysis. So basically, what is the demand? What is the capacity? No, all this, if it is deterministic, which means we know what is the actual demand, we know what is the actual capacity. So if all these things are known, so we can do a deterministic analysis, right? So we exactly know what will be the delay that will be caused, what will be the queue length, everything. So stochastic means we do not know how many vehicles will be using the facilities. Say it is random, or if the capacity of this location is random, right? So in those cases, we will go for a stochastic analysis because we cannot exactly say what will be the uh, delay or the queue length and so on. So we try to use random the probability theory to come up with expected values of these quantities. Okay, so that's what we were looking at in week number 3, right? So now let's move on into some problems. Okay, so I would recommend you to have a notebook and a pen and also a calculator because we'll be working out some numericals in this week. Okay, so just keep that handy. Okay, so the first question is, so this is related to the concept from week 3. So just as a quick revision, okay. So the K factor represents the proportion of AADT occurring during dash. So the options are the 10th peak hour of the year, 50th peak hour of the year, 30th peak hour of the year, and 25th peak hour of the year. Okay, so I have launched a poll, so you can answer in the poll or you can use the chat also. Okay, so we have one answer for option A. Any other answers? Okay, so the right answer is option C. It is the 30th peak hour of the year. Okay, so what is this K factor? So where did we use it? So we saw this concept of directional design hourly volume, right? So when we want to design a particular facility, so we design it for the peak hour condition, right? So because that's where we expect the capacity or the demand to be the maximum, right? So during the peak hour is when the demand is maximum. So that's the demand that we want to design our facility for, right? So, but how do we determine this? So we looked at different ways of measuring volumes, and one was this AADT, right? So annual average daily traffic, right? So this is an average value of the demand that we are that we have measured, right? So which means that the variation in the demand throughout the day is not captured by this, right? So during some hours we'll have values that are exceeding the AADT, and other hours it will be lesser than AADT, right? So therefore we cannot design using the AADT value. So then how do we calculate the directional design hourly volume? So that is by taking the AADT. So again, when measuring the AADT, we do not differentiate between the directional flows, right? So for both, we consider both directions of flows at a particular location, right? So therefore, when we are doing the DDHV, we are designing for the peak direction. So we have a directional split factor, okay, that is D, and then still this is for the daily average. So we need the peak hour, the proportion of traffic that will be seen in the peak hour. So that's where this peak hour proportionality factor K comes in, right? So this is nothing but, so what is the proportion of the total the average daily traffic? So that will be observed in the peak hour, right? So whether it will be 50%, 60%, or 70%, whatever it is. So what is that proportion that we will be observing in the maximum in the peak hour of the day, right? So that's the K factor. So what is the value that we will generally take is, say, so in AADT we are measuring all the 365 days and 24 hours, right? So that's what AADT means, right? So we measure for 24 hours for all the hours in all the days of the year, and then take the average of all this, right? So that's AADT. So which means we have 365 into 24, hourly, demand observations. Now what we will do is, put it in descending order, right? So we have these many observations, we put them in descending order, something like this, right? They have the demand, and this is different number of observations sorted in the descending order. So you take the 30th hour or the 30th value, okay? So which means that all these values, the 1 to 29, all these demand values are greater, right? So and everything after this will be smaller. So whatever this particular value is, let us call this D30, okay? So you take D30 and then you take the AADT. So that will be your K. What is the proportion of AADT that is observed in the 30th hour, right? So 30th hour is this K times of your AADT, right? So that is your K factor. So why do we take that? So why not just design for the maximum demand that we observed in the year? So because that is financially it is not viable. Why? Because this particular let us call this D max. So D max is observed only in 1 hour of the entire year, right? So that's it's very rare that we will be seeing D max in the throughout the year, right? So because it happens very rarely, and if we design our facility for that D max, so it's basically a lot of wasted resources for most of the year. The demand will never be equal to the capacity that we are going to use. So which means the facility will be over designed, right? So that's why so we do not always go for this maximum absolute maximum that we are observing. So we need to have some trade-off, right? So we cannot go too low as well. If you go too low, then for most of the year our facility will be congested, right? So that is also what we want, right? So that we have to strike a balance between the physical, the resources that we are going to spend, and also the service quality that we are providing. So that's where this 30th hourly maximum hourly volume is taken. So which means that only 29 times of the year, so there can be a higher demand than the capacity that we will be providing. So which means only 29 times we expect the facility to be congested, which is reasonably accepted. In the whole year only 29 times this occurs, right? So that is a fairly acceptable compromise that we are making, right? So that's the general rule that we use to pick out the proportionality factor. So therefore 30th peak hour of the year is the right answer. Okay, question number two is, suppose a detector records an occupancy of 0.35 for 15-minute analysis period, and the average length of a vehicle is 4.5 meters and the detector length is 107 centimeters. Then what is the density? So we need to find density from the occupancy. Any answers? Can we need more time or shall we look at the answers?
Sir, we shall look into answer, sir.
Okay. So the answer is the density is 62.84 vehicles per kilometer per lane. So, but how do we get this? So the relationship between density and occupancy is occupancy divided by the length of the vehicle plus the length of the detector. Okay, so that's the relationship between occupancy and density. Okay, so we know what the occupancy is, we know the average vehicle length, and we know the detector length as well, right? So we have everything that we need, we can calculate it. So what is the occupancy? That is given as 0.35, right? So which means 35% of the time of our analysis period there was a vehicle within the loop detector, right? So that's what this 0.35 is, divided by, so what's the average vehicle length? It was 4.5 meters, and the detector length was 107 centimeters, right? So we need to be careful with the units, we need to have everything in the same units. So that is 1.07 meters, right? So this will be 0.35 by 5.57 meters. So this would be what? 0.35 by 5.57. So this is 0.0628, right? So this is in what units? So this is in vehicles per meter, right? Because our vehicle length and detector length are in meters. So this is the density, per meter. So, but usually we express density, in vehicles per kilometer, right? So which means you have to multiply. This is in 1 meter, these many vehicles. So in 1,000 meters, that is 1 kilometers, it will be 62.8 vehicles per kilometer. So again, this is not just per kilometer, this is also per lane, because this detector, are usually installed in a single lane, right? So this occupancy is measured in one particular lane of the approach. So therefore, this is the density measured per lane of the whichever approach that we are measuring, right? So therefore, the density is 62.8 vehicles per kilometer per lane. Okay, so why do you go for this? Because see, this is an easier way of measuring the density, right? So because density is the number of vehicles in a stretch of the road. So if you want to directly measure it, so you have to observe the whole stretch, right? So which is usually very difficult, right? So to measure the very long stretch and then count the vehicles that are there, at a particular time. So that is a that's much more difficult than getting this occupancy value from a particular location, right? So this occupancy is coming from a given location on the road, right? So we have installed this loop detector and then measuring the time the vehicles are present within this loop detector in a given time period. So this is much more easier, right? That's why we go for getting the occupancy and then deriving the density out of it, right? So that's why we do this. Okay, any questions?
How did you convert it to lane, sir? That
So I
what?
didn't convert it. So what we already get, right? So this is also in vehicles per meter per lane only, because this occupancy, this 0.35 is for one particular lane. So it's already in one lane.
Sir, no, sir. That what did you done to convert them to 62.8?
Yeah, so that is, I just multiplied it by 1,000. Why? Because
Because
0.0628 is vehicles per meter, right? So in 1 meter, it is 0.0628 vehicles. So if you want in 1 kilometer, so 1 kilometer is what, 1,000 meters, right? So we have to multiply this by 1,000 to get it in vehicles per kilometer.
okay, sir.
Okay, I've just converted it from meters to kilometer by multiplying it by 1,000. Okay, any other questions? Okay, so moving on to question number 3. So this is coming back to week number 3 content. So we are looking at shock waves, right? So we have a signalized intersection as we discussed earlier. So we have this is our signal location, right? So we have some inflow. This is our demand or volume. Inflow, A is your inflow, right? So this there is some duration of red time, so that is creating some shock waves, right? So we have different kinds of shock waves that are created, right? So the question is, identify the type of shock wave formed between the traffic states BA, BC, and BD, right? So this is the first one, BA. This is the second one, BC. This is the third one, BD, right? So we have multiple shock waves, but we are only looking at these three shock waves between BA, BC, and BD. We want to say what is the type of each of these shock waves, right? So we have these options. So forward recovery, forward forming, rear stationary, backward recovery, backward forming, frontal stationary, and different combination of this. So you have to correctly identify. So which is the correct combination that is given here. Okay, so we have one answer as option C. Any other answers? Okay, so the right answer is actually option D. It is backward forming, backward recovery, and frontal stationary. Okay, so which are the three? So this is the first one, right? Let me use different colors. Let's take blue. So this is the first one, right? So between B and A, right? So this is the backward forming. Then we have between B and C. So here you have B and then C. So this is the shock wave separating traffic states B and C, right? So that is the backward recovery. Finally, we have BD, right? So we have B and D. So this is the state that is separating B and D. So that is the frontal stationary. Right? So these are the three shock waves that we are looking at. And that's just the right order: backward forming, backward recovery, and frontal stationary. But how do you remember all this? Right? So there is a simple way. So we have only six different types of shock waves, right? So one is, first you have to identify whether it is forward or backward. So that is depending on the I said it depending on that in which direction is the traffic state propagating. Is it in the direction of the traffic flow or against it, right? So if it is in the direction of traffic flow, it is forward, and if it is against the direction of traffic flow, it is backward. Okay, so here, what is the direction of traffic flow? It is in this direction, right? So this is our distance axis. The y-axis is the distance axis, and the traffic is flowing in this direction, right? So all the shock waves which are in this particular upward direction, so those are either forward shock waves. So which means what? So if you take a shock wave and calculate and look at its slope, if it has a positive slope, right? So here this is a positive one, this is positive, and this is positive. All these positive slopes are forward shock waves, forward moving shock waves, right? And then those with negative slopes, those are backward moving shock waves, right? And then we also have zero speed, so that can come in both forward and rear. For now, just understand. So this is basically positive means forward, negative slope means backward, right? So that's the first distinction that you have to make, whether it is forward or backward. Then we have, if it is forward or backward, then we have to determine whether it is stationary, forming, or recovery, right? So stationary is the simplest one. Stationary is basically zero slope. It means it will be a horizontal line between the location. It will be at the same location for that duration of time that shock wave is existing. So zero slope means it's a stationary shock wave. And then what is forming, and what is recovery? So we'll see it in this way. So first we look at forward. Okay, so for a forward shock wave, so if you have in the downstream direction, so which is, so if this is your distance, this is time. Okay, this is always fixed, distance and time. So which means this area is your downstream, and this area is your upstream, right? So if the density in the downstream location, if it is higher, and then low, this high low is all relative, right? So compared to downstream, if upstream is low, that's the condition that we are looking at. So in this case, it will be forward recovery, right? So this is for forward. So the other way, so forward forming will be the reverse. So if you have low on the downstream and high on the upstream, it will be forward forming, right? And this will be forward or frontal stationary, right? Zero slope. Now for the backward side, so for a backward shock wave, so if you have high on the downstream side, and low on the upstream side, so this will be a backward forming shock wave. Okay, so the reverse is for backward recovery. So low on the downstream, high on the upstream, so this will be a backward recovery. Okay, and then again you'll have a zero slope for rear stationary, right? So for stationary case alone, how will we say whether it is forward or frontal or rear? So for that, so if you have a stationary shock wave and you have low on the downstream side, high on the upstream side, so this will be frontal. So the reverse, if you have high and low, this will be real. Okay, so these are the six different shockwaves. So you just have to look at which on what is the traffic state on the downstream side and upstream side, and then what is the speed of the shockwave. Is it positive or negative or zero, right? So depending so this combination of speed and the two densities on the high on the either side of the shockwave, so with that you can determine it. So what we have here, so if you look at B and A, traffic state B, so this is a signalized intersection, right? So when during the red time, what is happening? So this is basically your stop line. So downstream is basically this side, and this is upstream. So in the upstream side, so you have jam density, right? So during the red time, so which means BA traffic state at B is high density, and traffic state A, so this will be lower than your jam density. Whatever is coming or approaching your signalized intersection, that is at a lower density. So which case it is? So that is basically this particular case, right? So here we have traffic state B, traffic state A. B is the jam density, so it is high, and A is the inflow, which is at a lower density. In comparatively to the jam density, it will be at a lower density. So therefore, the shock wave that is formed is a backward forming shock wave. Okay, so that is for B and A. So if you are looking at B and C, so again we know B is a high density jam density, and C is a lower density, right? So which is this case, right? So this is B, this is traffic state C. So B is a high density compared to traffic state C. So this is high and low. So it is a backward recovery shock wave. And finally, we were looking at the shock wave separating B and D, right? So this is this stationary portion. The slope is zero. So which means we have to determine whether it is a frontal or rear. So here we have D on the downstream side and B on the upstream side. So traffic state D and traffic state D. B is high density and D is low density, right? So because D is basically what? Zero flow, zero density, right? So when the signal turns red, so immediately upstream there is no vehicle crossing this stop line, right? So there is zero flow and zero density. That is traffic state D. But immediately upstream there will be jam density, right? So that's the condition. So it is low and high. So this will be a frontal stationary shock wave. Okay, is that clear? Any questions? Okay. So the first thing is, so when you are presented this shock wave diagram, identify what is the densities that are on either side of the shock wave, right? So which side is high, which side is low, comparatively, right? So when we are looking at uh, you know uh, pairs, so between B and A, so which is lower? A is lower compared to B, right? So along this boundary. But when you are looking at A and D, A is higher than D, right? So we have to look at it in pairs, right? And then for that pair, which side is high, which side is low. And then once you have identified that, so you have only 6 different cases that you have to compare it to and then determine what is the type of the shock wave. Okay, so if there are no questions, we'll move ahead. Okay, question number 4 is on a single lane approach to a signalized intersection, the effective green time and effective red time are 30 seconds each. The arrival rate of the vehicles on this approach is 360 vehicles per hour. The saturation flow rate is 1440 vehicles per hour of green time per lane. Assume that at t equal to 0, the signal has just turned red. Calculate the average delay for the arriving vehicles within one complete cycle. Okay, so this is just like what we looked at, the same condition. So there is a signalized intersection, some vehicles are coming, signal turns red, the vehicles will be stopped, they will be experiencing delay. And then once the signal turns green, so they flow at saturation flow rate, and after some time the queue will be dissipated. So during this period when the vehicles are being stopped, so they are experiencing delay. So what is the average delay? That's what we want to calculate. So you can take about 5 minutes for this one. Anyone completed? Any answers? Let me know if you need some more time. I can wait. Otherwise, you can look at the answer. Okay, so I think we can go for the answer now. So the answer is actually 10 seconds. Okay, that is the average delay in one cycle. And how do we get it, right? So basically, whenever you want to, solve these kind of, questions where where you want to calculate the delay, so you need to first draw this the arrival and departure curves. So what is the arrival and departure curves? So on the y-axis, so you'll have the cumulative number of vehicles that are entering that location, and the cumulative number of vehicles that are leaving that particular location which we are analyzing. In this particular example, it is a signalized intersection, right? So how many vehicles are entering into this intersection and how many vehicles are leaving this intersection. Okay, so that cumulative value of that, it will be on the y-axis, and your x-axis is the time axis. Okay, so over time, how many vehicles are entering and leaving. So that's the that will give you the arrival and departure curves. So in our example, so what do we have? So we have a signalized intersection, so which has a green time, effective green of 30 and effective red of 30 seconds, right? So which means one cycle of this signal is 60 seconds, right? And we have 30 seconds of green and red in each. And the arrival rate of vehicles on this approach is 360 vehicles per hour. So which means vehicles, the inflow to this intersection is constant, right? Every hour, 360 vehicles are entering this intersection. So this, orange line that we have here, so this is our, arrival curve. So which tells us how many vehicles are at a given point in time, right? At a given point in time. So the value on this will tell us the n is nothing but the number of vehicles that have entered this intersection, right? So that's what the arrival curve gives us. And what is the slope of this curve? So this is the arrival rate. So in our case, the arrival rate is 360 vehicles per hour, right? So that is the slope of this orange line, the arrival curve. And then the green line represents the departure curve, so which is how many vehicles are crossing this intersection and then going, right? So how many vehicles are crossing the signal, so initially, so we are assuming that for 30 seconds there is a red duration, right? So that's what we are taking, right? From t equal to 0 to t equal to 30, there is a red duration, so which means that no vehicle will be able to cross it, right? So that's why the slope of this departure curve is 0, right? So no vehicles are crossing. And then after 30 seconds, for the next 30 seconds, we'll have green time, right? So what happens in a signalized intersection? So once the signal turns from red to green, so you will have flow at saturation flow rate, okay? Because all this demand that has been accumulated, right? So that will be at jam density, right? So that will be at the maximum density. So once the signal turns green, so all this vehicle will be flowing at the capacity condition, right? So that will be at the saturation flow rate. And what is the saturation flow rate? It is 1440 vehicles per hour of green time per lane, right? So this is a single lane approach. Okay, so we have one lane and the saturation flow rate per lane is 1440. So the slope of this departure curve will be 1440 vehicles per hour. Okay, so because our the departure rate is higher than the the arrival rates. Arrival rate is 360, whereas the departure rate is 1440. So this slope is higher. So this is going to meet this particular arrival curve at some point, right? So that's where the Q dissipation occurs, which means so during this red time, some Q is formed in the signalized intersection, right? So vehicles are waiting. After some time, so whenever the arrival and departure curves meet, so all the vehicles that have been standing in the queue, so those have crossed, right? So after this point, so whatever time is remaining, so whatever vehicles that come, so they will be without waiting in the signal, they will be crossing, right? So that's when the arrival and departure curves are together. So no vehicles are waiting. So again, the signal will turn into red. Vehicles will again wait, and then when the signal turns green, they will be flowing at saturation flow rate. So this keeps on repeating every cycle. So So now what we want, so we want to calculate the average delay. So what is the delay from this curve? So let me just erase all this. Okay, so the delay is nothing but the horizontal difference, right? This is the delay between, so this is particular vehicle, right? So let us say this is the number 5, which is means for the fifth vehicle, right? The T1 is the time at which the fifth vehicle has entered the intersection, right? So that is the point on the arrival curve. So it arrived at the intersection at time T1 and it has left the intersection at time T2, right? So which means the difference between T2 and T1 is the time that the vehicle has spent in the signalized intersection, right? So that is the delay that is experienced by this vehicle. So if the signal was not there, this vehicle would have just crossed through, right? So it would not have any delay. But because the signal was red, so the vehicle had to wait T2 minus T1 seconds, right? So that is the delay that is experienced by this particular vehicle. So similarly, multiple vehicles, so each vehicle have their own delay, right? So that is given by the corresponding difference between the arrival and departure. So for the second vehicle, for the third vehicle, fourth vehicle, and so on. So, which means that if you calculate if you add up the delays of all these vehicles, so you will get the total delay. So which means the area of this triangle or the area of the region between your arrival and departure curve will give you the total delay, right? So area between arrival and departure curves is equal to delay, right? So provided you have removed the free flow travel time. So if the point at which you are measuring the arrival and the departure are different, then you have to remove the free flow travel time. But here we are considering the points to be the same point, right? So the arrival point and the departure point, the entry and exit points to be the same. So in that case, the area between the arrival and departure curve will give you the delay, that is the total delay, right? So here that is closer to what we want. So we want to calculate the average delay in one cycle. So we know how to calculate the total delay. If we can calculate the area of this triangle, so that will give us, so one cycle is how much? 60 seconds, right, in our case. So for these vehicles, in this period there is no delay, we know that, right? So the delay is only in this initial portion where this triangle is formed. So that is the total delay in this one cycle. And then we can also calculate how many vehicles will be arriving in this one cycle. So total delay by the number of vehicles, that will give you the average delay. Okay. So average delay in one cycle is equal to total delay TD divided by total number of vehicles arriving in the cycle. Okay, so these are the two things. So for average delay, we need to calculate the total delay and the total number of vehicles that are arriving in the cycle. So if we can calculate those two, so we can calculate the average delay. Okay. So how do we calculate that? So we know, so which means we need to find out what is this point, right? So when do these two meet? Okay, so we know this is 360, the slope, and this slope is 1440. Okay, so the equation of this arrival curve is what? So let us say the y-axis is n and the x-axis is t. Okay, so then n is equal to 360 t. Okay, I will take the time in hours, because what is the unit of 360? It is vehicles per hours, right? So t should be in hours. Okay, so n is equal to 360 t. That is for our arrival curve. Okay, this is our arrival curve. So for the departure curve, what is it? So for initially for 30 seconds, the slope is 0. After 30 seconds, is it n is equal to 1440 t plus some constant a, right? So what is this constant a? So we know one particular point in this departure curve, which is 30 comma 0, right? At time equal to 30, the number of departures is 0. So we know that, so we can substitute that here. So n is equal to 0 at time is equal to 30. but we need to take this in hours. Okay, why? Because our slope, the unit of that is in hours, right? So 1440 into 30 seconds converted to hours, that plus a, so a is minus 1440 into 30 by 3600. So this is our departure curve. N is equal to 1440 t minus 1440 into 30 by 3600. Okay, so now to find out when the the queue clears, right? So it is nothing but wherever these two arrival and departure curve are intersecting. So we need to find the point of intersection. So for that we need to equate the arrival curve with the departure curve. That will tell us where they meet. So 360t is equal to 1440t minus 1440 into 30 by 3600. Okay, so if you solve this, you will find that t is equal to, it will come out to be 0.011. Okay, this is in hours, which is equal to 40 seconds, right? So which means that after once the signal turns green, so this is happening at 40 seconds. So in 10 seconds, whatever is the queue that is formed will be completely, dissipated. Okay. So it takes 10 seconds. So in total, 40 seconds from here, 0. But after the signal turns green, in 10 seconds, all the queue will be clear. So this is one part, right? So we know this point is 40, comma something, right? So yeah. So what is the y for that? So n of 40 is equal to, from the arrival curve we can know that point, right? So because both arrival and the cumulative number of arrivals and departures is same, so we can use either equation 1 or equation 2. Equation 1 is simpler, so I'm going to use that. So it is 360 into 40 by 3600. Okay, so that is the number of, so I'm not simplifying it, right? So that is the number of vehicles at this point. So we know that point, right? So this is the triangle. So we need so we have everything that we need to calculate the area of triangle. So area of triangle 1 is nothing but half into, so the base of the triangle is 30 seconds, right? So 30 divided by 3600 into, what is the height of this triangle? So that is what we calculated here. So it is 360 into 40 by 3600. Yeah, so this is basically 10 times the, right? So this is 4, right? So height is 4. So half into 30 by 3600 into 4. So that is your area, right? So now we need, so we have the total delay. So this is also equal to total delay. Okay, so but what we want is average delay, right? So average delay in the whole cycle. So average delay equal to total delay by number of vehicles. So what is the number of vehicles that will arrive in one cycle? So for that we have to look at the arrival curve. So that is basically equation number 1. So arrival curve is 360t and cycle time is, I will write n cycle, number of vehicles in one cycle. So that is 360 into, one cycle is 60 seconds in this case. So 360 by 3600. So which is basically 6 vehicles. So 6 vehicles arrive in one cycle, right? So the average delay will be, so whatever is the total delay, so half into 30 by 3600 into 4 whole divided by 6. So the numerator will be actually 60. So this is 10 seconds. Okay, so that's how we get the average delay of 10 seconds in this whole cycle. So we have 6 vehicles that are coming in, right? So each vehicle has a different number of different delay experience, right? So the vehicle that came exactly at the start of the green, so that experiences the longest delay, right? So it will wait for the whole 30 seconds. So the vehicles that arrived later, so they will be waiting for a smaller and smaller amount of time, and the vehicles that came after the queue dissipated, they have zero delay, right? But on an average, the 6 vehicles have a 10-second delay, right? So that's all that we have to do for this particular question. Okay, any doubts? Right, so the thing that you need to remember is, so you whenever you want to calculate delay, draw the arrival curve, draw the departure curve. Okay, and then the area between the arrival and the departure curve will give you the total delay. Okay, and then find the total number of vehicles for the average delay. Find the total number of vehicles that have used this facility in the given period. So that is basically in our case in one cycle, right? So in 60 seconds, number of vehicles, this is our end cycle that have come, right? So that we can calculate from the arrival curve. So using that total delay and the number of vehicles, we can calculate the average delay, right? So that's all that we have done here. Okay, so if there is no doubt, we can move on to the next question. Okay, question number 5. So this is with respect to the shock waves. Okay, so the speed of the shock waves. So the traffic stream on the road is assumed to follow the Greenberg's model. Okay. A shock wave is developed when a stream moving with optimum density Ko is stopped. This shock wave is moving upstream at a speed of 35 kilometers per hour. So determine the stream speed at maximum flow. Okay, I'll just give you clue or to help you recall. So how do we calculate the shock wave speed? So if you say the shock wave speed is u, or let us say WAB, right? So that is the notation that is used in the lectures. So the shock wave separating the traffic state A and B, the speed of it is given by QA minus QB by Ka minus Kb. Okay, so Qa and Ka are the flow and density at traffic state A, and Qb and Kb are the flow and density at traffic state B. So if you know those two, so you can basically this is the slope of the line connecting traffic states A and B in the fundamental diagram. Right, so that's how you calculate the speed of shock wave. Okay, so that's what you need to use to solve this particular question. Okay, again you can take 4 to 5 minutes. So you need to know the Greenberg model. So I can give you that as well. So in Greenberg model, how is the speed and density related? V is equal to VO log of Kj by K. Okay, so VO is the optimum speed. Okay, not the free flow speed. So that's the Greenberg model. So these two things you can use and then you can solve this. Any answers? Should we wait for a little more time or shall we look at the answers? Okay, so yeah, so we'll look at the answer. Okay, so here we are looking at analyzing a shock wave, right? So let's first understand what are the traffic states that are involved, okay, in this particular shock wave. So we are looking at a particular a road, okay, a road stretch, right? So let us say this is the location where the boundary is existing at some particular point of time, okay. So this is our shock wave boundary, right? So a location where the shock wave is developed, okay. So what we know, so it is developed when a stream moving with optimum density is stopped, right? Which means upstream of this location, so we have a density K0, right? So this is at the optimum density. What is the optimum density? Where the flow is maximum, right? So that is the traffic state. Let us say A, and this is traffic state B, okay? So it is stop. Stop means what? So it is going to you know, jam condition, right? So it is coming at optimum density and then it is suddenly stopped, right? Right, it's not, sorry, not jam condition. It is uh, yeah, it is jam condition. So because there is congestion existing, so this inflow cannot move further, so they have to come to a stop, right? So jam condition exists. So these are the two traffic states that we are looking at, traffic state A and B. And because the densities are different, so when these two traffic state meets, a shock wave is developed, right? So this is the upstream of this location of the shock wave, and this is your downstream location, okay. Now what else do we know? This shock wave is moving upstream at a speed of 35 kilometers per hour, right? So the shock wave is moving in the upstream direction at 35 kilometers per hour, right? So if it is moving upstream, what does it mean? It is a backward shock wave, right? Because it is opposite to the flow of traffic, right? So traffic is flowing in this direction, right? So downstream is the direction in which the traffic flows, but this shock wave is moving in the upstream direction, which means it's a you know backward shock wave. So you can also see that if you draw the fundamental diagram, so you will know. So this is qk. So what is k0? K0, I said it is the density where flow is maximum, right? So this is your traffic state A, and this is your traffic state B with jam density kj, right? So if you connect these two, what do you see? You see a negative slope, right? The slope is negative, which means it's a backward forming shock wave, okay. So that also we know, and the speed, this slope is 35, right, minus 35. So what we want to know is determine the stream speed at maximum flow. So what is the stream speed at maximum flow? So we know maximum flow is happening at the traffic state A. So we want the stream speed, not the shock wave speed, stream speed. So how do we find the stream speed? So when you have the QK diagram, so the stream speed at any traffic state can be obtained, if you connect the origin, to the given state and find the slope, right? So that will give you the stream speed at the traffic state, okay. So this is applicable for any state, right? So if you want the stream speed at jam density, it will be connecting origin to kj, so which means zero slope, right? So we know that speed at jam density is zero, right? So that's what we want. So at traffic state A, which is maximum flow state, what is V0, right? So that's what we want to find out. So how will we do this? So we will make use of the information that is given to us, which is the speed of the shock wave minus 35. So how do we write this shock wave speed? So that's what I gave here, this WAB. And what is A and B? A and B are these two traffic states, okay. So we know A is K A, traffic state A is the optimal value, and then KB is equal to KJ. Okay, so we know from the Greenberg's model, so V is equal to V0, VO log KJ by K, right? Uh, yeah, and you know what is Q? Q is equal to KV, right? Which is equal to V0 K into log of Kj by K, right? So we just multiplied V with K and then we got the equation for Q. Okay, so now what we want to do? So we want to find WAB, so which is Q at A, so which is Q of K0 KO minus Q at jam density divided by difference in the densities KO minus KJ, right? So what is Q of KO? So that is nothing but VO KO log of KJ by KO. Okay, I'm just substituting it. And then what is Q of KJ? That is 0, right? At jam density, flow is 0, we know that. So divided by KO minus KJ, right? So this is the speed of the shock wave. So here again, we do not know what is KO, right? So but we can find that, express it in terms of KJ, right? So how do we do that? How do you find the maximum density? So in the last week, we saw how to find the maximum value of a function, right? So we know Q as a function of K. Q is V0 K log Kj by K, right? So to find the maximum, so we differentiate it with respect to K and then set it equal to 0, right? So if you differentiate this, set it equal to 0. So I'm not going to derive it. So it is easy, you can do it in your free time. So K0 will be Kj by E, right? So it happens at the location at that density where it is equal to 1 by E times the jam density, right? So this is for the Greenberg's model, right? So if you look at, if you remember, like for the green sheet model, the optimum density will be at the midpoint Kj by 2. But for a Greenberg model, the maximum flow happens at the jam density by E. Okay, so you can remember this. It's also easy. You can derive it later and then verify it. Okay, so we know Ko is Kj by E for the Greenberg model. So I'm going to substitute that. So it will be Vo into Kj by E. So log of Kj by E divided by Kj by E minus Kj. Okay, so if you simplify that, what will we get? So log of Kj by E, so that is 1. Okay, so because Kj gets cancelled, so log E will be 1. So numerator we have V0 Kj by E, denominator we have 1 minus E times Kj by E, so this will be nothing but V0 by 1 minus E. Okay, so Kj by E got cancelled in the numerator and denominator. So what is this V0 by 1 minus E? Is nothing but the stream speed, right? So that's what we have derived till now. So WAB, so the stream speed is VO. So VO is what we want to find, right? So stream speed at the optimal density or the maximum flow. So divided by 1 minus E, and we know what is WAB, right? So that is given to us. That is the stream speed, which is 35 kmph. But can we put 35 directly here? No, because this 35 kmph is moving in the upstream direction, right? So we need to take care of the sign as well. This is a backward moving shock wave, right? So therefore it is not 35 but minus 35, because it is a backward moving shock wave. It's a negative slope, so equal to V0 by 1 minus E. So E is a constant, so we don't have any other variable here. So the optimal density is, so optimal speed is minus 35 times 1 minus E. So that will be 60.14 kmph. Okay, this is the speed where the flow is maximum. Okay, basically the slope of the line that is connecting origin to the traffic state A. Okay, so that's what we also wanted to find the stream speed at maximum flow. Any questions? Okay, so if there are no questions, we'll move on to the next question, which is question number 6. The traffic stream on the road is assumed to follow the given speed density relationship. Okay, so where V is equal to Vf minus Vf by kj squared into k squared, right? So here Vf is the free flow speed, kj is the jam density. Calculate the speed of the shock wave that develops when a stream moving with a density alpha kj meets a stream moving with density 1 minus alpha times kj, where alpha is less than zero point 0.5. Okay, so here we are not looking at any standard models, right? So we have a different vk relationship, right? So that is given here, and the two traffic states. So similar to the previous question, so two traffic states A and B, but here it is not something that we know like critical density or anything. So it is some alpha times kj, so that is in the upstream direction, and 1 minus alpha times kj, that is the state in the downstream direction. So when these two states are meeting, a shock wave is developing, and we need to calculate the speed of this shock wave, right? So exactly the same procedure that we did, but with a different fundamental diagram. Okay, so again you can take 4 to 5 minutes, and then we can see what the answer is. Any answers? All right. So here you can look at the answer. So, so the answer is alpha times 1 minus alpha times Vf. Okay, but we'll follow the same procedure exactly. Okay. So to find the speed of the shock wave, so separating traffic states A and B, so we know it is QA minus QB, right? Ka minus Kb, right? So that's all. So we need to know these four numbers QA, QB, Ka, Kb. So then we can find the speed. So here, what are the two traffic states? So we are given that, so let us say this is the location where the two traffic states meet. Okay, so A and B. The traffic state A is some alpha times Kj, and B is 1 minus alpha times Kj, right? So Kj is fixed, right? So for this particular road, so it is some constant, so Kj. And so we have alpha times Kj and 1 minus alpha times Kj, and we also know, or given that alpha is less than 0.5, right? So that, what does it mean? Which means Ka, traffic density at A is lesser than density at B. So in other words, the shock wave that is generated is a backward moving, right? So which means a low density traffic state is meeting a high density traffic state, right? So it is going to generate a shock wave in the negative direction. Okay, in the which means it is going to move in the this traffic state is going to propagate in the upstream direction. Okay, so we know we are given the relationship as well. So V is equal to Vf minus Vf by Kj square into K square. Right? So that's the relationship, Vf minus Vf by Kj square into K square. So because we need Q, right, to sphere to calculate the shock wave speed. So let's write what Q is. So Q is nothing but K into V. Okay, so we know V, so we multiply it with K, so we get Vfk minus Vf by Kj square into K cube. Okay, so this is Q as a function of K. Okay, now so let's find WAB. So what is QA? QA is uh, so the density, so Ka is equal to alpha Kj. Kb is 1 minus alpha Kj. Okay, so let's not substitute them right now. Let's write it in terms of K and Kb itself. So Vf into, so when we take the difference of QA minus QB, we'll get Vf into Ka minus Kb. Okay, minus Vf by Kj squared into Ka cubed minus Kb cubed. So all divided by Ka minus Kb. Okay, so this is the speed. So initially, so let's simplify this. So if we just separate this, I will have Vf. So Ka minus Kb will get cancelled for the first term. So minus, so Vf by Kj squared. So A cubed minus B cubed is A minus B times A squared plus AB plus B squared, right? So divided by Ka minus Kb is still there. So again, 1 Ka minus Kb in the numerator and denominator will get cancelled. So we'll have Vf minus Vf by Kj squared into Ka square plus Kb plus Kb squared. Okay, so let's move on to the next page. So far what we have is Vf minus Vf into Ka squared plus Ka Kb plus Kb squared. Okay, so let's substitute now Ka and Kb values. So we have minus here by Kg squared. So what is Ka? Ka is alpha times Kj, right? So alpha squared Kj squared plus alpha Kj into 1 minus alpha Kj plus 1 minus alpha squared Kj squared. Okay, so just have to simplify this. So, we have 1 alpha square Kj squared plus, take the product of this, you will have alpha Kj squared minus alpha squared Kj squared plus Kj squared alpha squared Kj squared minus 2 alpha Kj. Okay, so 1 alpha square Kj square and minus alpha square Kj square gets cancelled. So from the remaining terms, so we can take so here will be Kj square actually. Okay, so the Kj square in the remaining terms will get cancelled. Okay, and so minus 2 alpha and then there is a plus alpha, so it will be minus Pf times. So what will be remaining is okay, so this finally reduces to Pf into alpha into 1 minus alpha. So this is the shock wave speed that is separating the two traffic states. Okay, so Vf is your free flow speed, that is a constant. So alpha and alpha, so alpha is also another constant, so that is not given to us. It's only less than 0.5 that we know, but all these are constants. So finally, the speed of the shock wave is Vf into alpha into 1 minus alpha. Okay, so that's the speed of the shock wave that is separating those two boundaries. Okay, so exactly the same thing that we did, but for a different, fundamental diagram. So the next question is 7. The following speed density relationship is found for a highway segment. Okay, so V is 0.001 times K minus 200 the whole square minus 1.5. LP is the speed in kilometers per hour and K is the density in vehicles per kilometer. So we need to estimate the free flow speed, the jam density, the speed and the density at the maximum flow, and also the lane capacity. Okay, so this is a much simpler one. Okay, so maybe 3 to 4 minutes. Actually, you need to estimate all these quantities. It's not an MCQ, so you need to find out what is the value of free flow speed, value of jam density, and so on. So what's the free flow speed? So what is the answer? What is the speed and density at maximum flow? It's not an MCQ. It's a numerical problem. So you need to solve and find out the value of all these four quantities: value of free flow speed, value of jam density, value of speed and density at the maximum flow, and the capacity. You need to calculate it. Any answers? Okay. So these are the answers. Okay, so free flow speed is 38.5 kilometers per hour. Jam density is 238.73. The speed at optimal flow is 17.26 and density is 63.02 and then the lane capacity is 1087.95. Right, so but how do we obtain this? So the relationship between speed and density is V is equal to 0.001 times k minus 200 squared minus 1.5, right? So this is the speed density relationship. Okay, so what is the free flow speed? So Vf, the free flow speed, is nothing but the speed at zero density, right? So V of zero, when density is zero, whatever is the speed you have, that's the free flow speed. So basically we have to substitute, k as zero to get the free flow speed. So that is nothing but 0.001 times 0 minus 200 squared minus 1.5, right? So you solve this, you'll find that Vf is equal to 38.5 kilometers per hour. Okay, so that's how you get the free flow speed. So the next question was to find out the jam density, right? So we represent it as kj, right? So what is jam density? At jam density, what do we know? At kj, comma v is equal to 0, right? The speed will be 0 when the density is equal to jam density. So which means that we need to substitute. So v of kj is equal to 0. So that's what we know. So what is v of kj? So it is 0.001 times k is actually kj now. So kj minus 200 squared minus 1.5. So this is equal to 0, right? So from here, you can simplify it. So we'll find what kj is, right? So kj minus 200 squared is nothing but 1.5 by 0.001. So kj is root of this plus 200. So that is 238.73 vehicles per kilometer. Okay, so that's the jam density, right? Any questions in these two? How do you find the free flow speed and jam density? Okay, so the third question was to find what is the speed and density at maximum flow, right? So which means we need to first get the equation for the flow and then we need to find out where the flow is maximum. Okay, so how do we get the equation for flow? So we know Q is related to K and V like this. Q is equal to KV, right? So we know the relationship between KV, right? So we can get Q. We have to multiply the speed density equation with K. Okay, so that will be 0.001 K into K minus 200 squared minus 1.5 K, right? So this is your density speed sorry flow density relationship. So we want to find where the flow is maximum. So how do you find the maximum function? So I looked at it multiple times, so we have to differentiate this equation with respect to k and then set it equal to 0, right? So that will tell you where this function is either the maximum or minimum. So here we will find out the maximum. So so when you solve this, so what you will get, so we have to differentiate this. So q is 0.001 k. So you have to expand this k cubed minus 40,000 into this. So that will be like 40k squared minus 400k. So minus 0.4k minus 1.5k, right? So this is here, QK relationship. So if you differentiate this, so you'll have 0.003 k squared minus 80k minus 0.4 minus 1.5. Okay, so you equate it to 0, you solve this quadratic equation. Okay, so you will find the roots, right? So k will have two roots, right? So the two roots will be 203.65, 63.02, right? So these are the two inflection points, right? So either the function will be maximum or minimum, at these densities. So you need to find that density where the flow is maximum, right? So you have to substitute these two values. So q at 203.65 and q at 63.02, right? So if you substitute this back into that equation, what you will find is q at 203 will be minus 302.76, and at 63 it will be 1087.947, right? So this is the density where the flow is maximum, right? So this is the density that you want, 63.02. So that is one of the answers. So density is 63.02. So we also need the speed at this maximum flow. So which means in the speed density relationship, we have to substitute the maximum density, the density at maximum flow, so which is V of 63.02. That is 17.26. Okay, and finally, so we have to find the lane capacity. So what is lane capacity? Basically, capacity is the maximum flow that you can accommodate, right? So what is the flow at the max, at the critical density, or the density where the flow is maximum? So that we have already calculated it, which is q of 63.02. So that is 1087.947, right? So that is your the lane capacity. So it is 1087.95 vehicles per hour. Okay, so that's how we calculate these different points in our fundamental diagram. Okay, so given a fundamental relationship. Okay, so with that, we are coming to the end of this week's session. So week number 3. Okay, so where we looked at the shock waves and the queuing analysis. Okay, so if you have any questions, so you can post it in the discussion forum for this course, right? So and then so that will be answered there. And for the next week, we'll again meet on Saturdays 4 to 6 p.m. Okay, thank you for attending. So we'll meet again next week.